So now let's consider the case of what is the correct size for the tree. Of course, we've discussed this under classification trees as well, and this is called overfitting. Okay, suppose you build a tree and the tree looks like this. Huge number of leaf nodes, massively complicated tree, right? Then of course we ask the question, is this tree too closely tied to the data that you have, or the training data that we have, right? So are we overfitting? Right now, the problem with creating a tree that is too big is that the tree might be very closely tied to the training data that we have. Right now, again, as we have discussed earlier, the training data has genuine data, which is representative of what we can expect when we deploy the model. And the training data also has some anomalous data, right? That is, things which are not usual, things which are not normal. But again, it'll exist. When you have a large data set, you'll have all kinds of crazy things in the data. Now, when you start building a tree that is very big, what will start happening beyond a certain point is that you will start creating rules for anomalous things that exist in the data set, in addition to the representative things that exist in the data set, right? So that's not a good thing. You want to create rules only for things which are representative of reality, not for crazy, unusual things that just happen to be in the training data. Okay, so when you start doing that, that is what we call as overfitting. Now to explain that diagrammatically, right, so let's consider the number of splits which represents the tree size, right? The more the number of splits, the more the number of leaf nodes. Okay, so as the number of splits increases, then your deviance on the training data will keep on reducing, right? That is natural. In fact, it's even easier to see in the case of regression than in the case of classification, right? That is because if you take a set of numbers, you will have a certain amount of deviance. You split it into two sets. The two sets into which you split will generally have lower amount of deviance, but in no case can the amount of deviance increase with these two new sets. Okay, so as a result of that, if you want to get the best performance on the training data, you should keep on building a tree that's larger and larger and larger, right? Build a tree that is as big as possible. That will give you the minimum deviance overall. Okay, and of course, minimum error rate as well. Okay, but that's not a great idea, because what will happen is if you look at independent data or your test partition, then up to a certain point, which is, remember, the x-axis is the size of the tree, up to a certain point, your performance on independent data will also improve, right? But after a certain point, when you start overfitting, that performance will start to deteriorate. The deviance or the error will start increasing, right? Or you can think of it as deviance, or you can even think of it as RMS error if you like. Okay, it's some measure of error. Okay, so what we are really looking for again is this point, right? So theoretically, that is the point at which the performance on independent data, unseen data, is the best, right? So ideally, what we are saying is we want to build a tree which is of that size. Okay, so that's really what we want to try and do. So for example, so we want to do this, choose a tree corresponding to this. Of course, you understand that given a set of data, you can have trees of differing sizes, which is number of leaf nodes. So for example, it is perfectly possible for us to have a tree which has only one leaf node. That's just the root node, right? That's just the root node, just the root node with all the training cases there, and your prediction is the average, which means no matter what the predictor attribute values are, you will always predict that the expenditure will be 592. It's the average prediction. This is again the equivalent of the naive model for regression. You just predict the mean, right? So your tree with one leaf is nothing but the naive model. Now you could have a tree with two leaves, which is just one split, right? So income less than 95,000, that's your tree. So you're going to go only on income. If income is less than 95,000, you will say less than equal to 95,450 or whatever the value was. Then you will say the predicted expenditure is 483. Otherwise, you will say the predicted expenditure is 754. Okay, so that's it. So that's a tree with 2 leaves. Obviously, this tree is not going to be very accurate, but it'll still probably be better than this tree. Okay, you could have a tree with 3 leaves, which is this, right? So it's the income less than 95,000, family size less than 2.5, your prediction is 410. If income less than 95,000, family size is greater than 2.5, your prediction is 536. If income is greater than 95,000, your prediction is 754. That's it. That's your complete tree, right? So you could have a tree with 3 leaves, you could have a tree with 4 leaves, and so on. Okay, that's a tree with 5 leaves. This is a tree with 6, and another with 8, with 9, and with 10. Okay, so you've got all of these 10 possible sizes for the trees. Okay, up to 10 possible. So you could have 1 leaf node, which is just the root node, or you could have 10 leaf nodes, right? And everything in between. So out of these, which is the optimum, right? That's what we want to try and find out. Okay, so what we are talking about is you've got all these trees possible. We ask a question, which tree size corresponds to this point? We want to find that, right? And then use that tree because that is the best tree.